Hello, Math 30-1 students. I believe we are on lesson 3 today. Fairly certain that's pages 9 or 10. We'll get to that in a second. Let's just go back to our very first page and make sure that we have an understanding of what's been going on lately. All right, so we have paid attention to H and K. H is a horizontal movement. H is a horizontal translation. H is backwards. X minus 3, 3 to the right. X plus 4, 4 to the left. K, K is going to be the vertical. K moves us up and down. K makes sense. Plus 7, up 7 units. Vertical translation, vertical shift, vertical movement, up 7 units. Minus 11, vertical translation, vertical movement, vertical shift, down 11. So let's make sure that we understand that H influences the X's, left and right. K influences the Y's, up and down. I believe that last lesson we talked about some reflections. When the A value is negative, that is a reflection over the X-axis. It influences Y. We're going to learn more about this in a couple seconds, actually. A influences Y. A and K are Y issues. When B is a negative, that influences X. Notice how B and H are so close to X? They're X issues. When you got a negative B, that's a reflection over the Y axis. What was a positive X will become a negative X. What was a negative X will become a positive X. Today we are going to learn about vertical and horizontal stretches. We are going to take something, not necessarily move it up and down, but we're going to stretch it taller or shorter. Or if we play around with the B value, that's a horizontal stretch. We can make things wider or more narrow. The joke I often give is that my B value is causing me to be a little on the wide side. I'll come back to that joke in a little bit. All right, so I think we're down here on page 9 or 10 or something, so let's figure out where we are. Where the heck is lesson 3? Come on, you can do it. There she is, lesson 3. All right, so we're going to develop an understanding of the effects of a vertical and horizontal stretch. All right, so we are playing around with the A value. So the first thing I want you to understand is that in this section, we are talking A. And I've already mentioned that A is going to influence Y. And here's the reason. Take a look. You put some value into X, and a Y comes out. Well, here, you're going to put that value into X. Your Y will come out, but then you're going to multiply it by 2. I can tell you that this is a vertical stretch by a factor of 2. This is a vertical stretch by a factor of 1/2. So what does this mean? Whatever the function was, this guy is 2 times taller. Whatever the function was, this guy is half as tall. All right, so take a peek here. Let's draw x squared minus 1. Not a problem. When I put in negative 2 squared is 4. 4 minus 1 is 3. So I get a 3 right here. Negative 1. Negative 1 squared is 1. Minus 1 is 0. Put a 0 in here. 0 squared is 0. Minus 1 is negative 1. Put a 1 in. 1 squared is 1. Minus 1 is 0. Oh, I see where we're headed here. And putting a 2 in, 2 squared is 4, minus 1 is 3. So you don't have to, but if you feel like it, negative 2 comma 3 is right about there. Negative 1 comma 0, oh, nice little x-intercept. 0, negative 1 is right there. No big surprise. Look at that y-intercept of negative 1. And then this thing is here, and then this thing is here. And just because I feel like being good, let's put a 3 in. 3 squared is 9, minus 1 is 8. So this thing's going to go here, bada bing, and this guy's going to go here, bada boom. And if I can do this, I apologize for the crudeness with my mouse, But this quadratic looks something like this. Oh, we can do better than that, but that's all right. All right, so there's our quadratic. Now, all this is saying is multiply the y values by 2. We are vertically stretching this thing. So grab this guy by the bottom and stretch him by a factor of 2. Grab this guy by the top. I realize there is no actual top, but imagine grabbing this thing, grabbing it by its head and its feet, and then pulling it 2 times taller. So a 3 will become a 6. A 0 multiplied by 2, well, that stays a 0. Negative 1 times a 2 is a negative 2. A 0 times a 2 is a 0 still, and a 6. So what would this guy look like? Well, negative 2 comma 6 is there. Boom. Oh, we have a name for this. It didn't move. It's invariant. Negative, what is this? Why do I have a, oh yeah, my bad. And then at 0, we're at negative 2. That's better. Sorry, I was just looking at the wrong thing. Another invariant point right here. And then at 2, we become 6. And before, where this thing would have been a nice little 8 up here, it's going to come way up here to 16. So now this thing looks something like this. That's better. Woo! Something like that. All right. So all that's going on then is that we happen to have a nice little vertical stretch by a factor of 2. All right. So I just got to see if we can. Okay. I don't know if I can. There. Turn off things on my computer. Sorry. A couple things popped up. Now, this guy is a vertical stretch by a factor of a half. Now, what does that mean? 3 is going to become 3 halves, or 1.5. That's not a negative. That's just a really big 3. 3 halves. Woo! That is an ugly 2. 0. Half of 0 is still 0. Half of negative 1 is negative a half. Half of 0 is still 0. And half of 3 becomes 3 halves. So what this means is all my y values got cut in half. So where I used to be at 3, now I happen to be at 1.5. I am still here at 0. That negative 1 became negative a half. Still at 0. And then I'm up here right there. So now this thing is going to look like this. Ooh, I missed that. Let's see if I can do that better, Mr. Chandler. There she is. Hit these points a little bit better. There it is. I'm sorry, but you get my point. All right? So what I want you to realize is that A is a vertical stretch. A being big means I want you to become taller. Notice how purple, and I admit technically these things go on forever, but notice how purple is getting to infinity faster. All of these graphs are getting there. This graph of x squared minus 1 will get to infinity. He's just getting there 2 times faster. He's just getting there half as fast. All right? So A influences Y. If A is negative, we would have reflected over the x-axis. A and K, K, we use K. My apologies. In 20, it's PQ. In 30, it's HK. And I always have to think about what course I'm teaching. A and K influence Y, and they both make sense. It's B and H that are the weird ones. Now, why are these points invariant? Because what's the definition of an x-intercept? The definition of an x-intercept is where y is 0. Well, I don't care how you stretch 0. You just get a bigger 0. Or you get a smaller 0. But you still get 0. Thus, the invariant points on a vertical stretch, whether you're taller or shorter, will always be the y-intercepts. So, what does the effect of putting a coefficient in front of the function have when the coefficient is greater than 1? When your a value is bigger than 1, you are a vertical stretch. You become taller, bigger. What effect does putting a leading coefficient in front of the function have when you're between 0 and 1? There's my green guy. You become shorter. Notice they didn't say negative here, because negative, all a negative does is just turns you upside down. It reflects you over the x-axis. Identify the location of invariant points. Yeah, we discussed this. The invariant points are always the x-intercepts. Again, how come? Because the definition of an x-intercept is when y is 0. Go ahead and stretch 0 all you want. You ain't changing it. Given a graph or a point on a graph, how would you determine the coordinates of the new points on any vertical stretch that's occurred? Simply multiply the y by the a value. Notice that all my y values here got multiplied by the a value. All the y values here got multiplied by the a value. Realize that a has no influence on x. All right? If you were to grab me by my feet and my head and stretch me 3 times taller, sure, I'd be over 18 feet tall. But the location of my nose, the location of my belly button would still be on the same x point. You're just going to pull me taller, but you're not moving me left and right. You're not doing anything horizontally. So notice that this only touches y's. All right, well, there's page 10. Let's move on here. Okay, now, Diploma loves this. I have mentioned you can only talk transformations when you have y equals. If they had tried to put a y plus 3, you know full well that I would have moved that across and made it a minus 3. Here they've made it a multiplying 3y. Well, how do you get rid of a multiplying 3? Well, you are going to divide by 3. So do not play around. If they try and mess with you by putting some value in front of y or behind y, you say, no, 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 no. We are not going to play around with this. Thus, this is clearly a vertical stretch by a factor of 1/3. All of my y values are now going to be 1/3 what they used to be. You see this 6? It's coming down to a 2. Notice, no change in the x value. You see this 3? It's coming down to a 1. You see this 0? It's staying right there because 1/3 of 0 is still 0. This -3 is about to become -1. This -6 is about to become -2. And this -9 is about to become a -3. Notice that this fairly tall function, now, if I can connect some dots here, I didn't do too bad with my mouse. Notice that this function is now 1/3 as tall as it used to be. Vertical stretches A have no influence on x. They only touch the y. Draw the graph of the transform function. State the coordinates of any invariant points. No problem. Take a look at this x-intercept, because invariant points on a vertical stretch are always the x-intercepts. I believe that that is -3, 0, and purple is going through -3, 0. So state the coordinates of any invariant points. I believe the invariant point is at -3, 0. All right. Now, it didn't discuss it in this question, but let's just have some fun. Would you agree that the domain, the acceptable x's, are from -6 up to 4? And on purple, the domain is -6 up to 4. Notice that vertical stretches don't touch x, so the domain is unchanged. my range was from -9 to 6 on the original. The new range is from -3 up to 2. A influences Y's only. All right, what do we got here? We got some point Z, 3, -8. It's on the original function. What happens when we have a vertical stretch of 1/4? That means that we are now 1/4 the height that we used to be. What does A influence? Y values. Meaning 3 does not change, comma. Now, -8, we're about to be 1/4 of what we used to be. I do believe that we are -2 is going to be the answer. Now, I'll share something with you. Classic diploma question would have been, make this divisible by 4. So maybe that 3 had been a 4. So pretend that the original point had been 4, -8. I'm totally changing the question. Let's pretend that was the original point. Well, if we do this, clearly this is going to be the answer. Yeah, I admit it's going to be 4 here, okay? But if they make it a multiple choice, then one of the multiple choices is going to be 4, -32, in case the kid multiplies by 4. One of the answers is going to be 1, -8, for the kid who thinks it influences the x. Maybe one of the multiple choices is going to be 1, -2, for the kid that thinks it affects both. So I've totally seen the diploma make these numbers both divisible by this thing right here, and so then they can give a nice set of distractors. So no problem. We know that A is going to influence Y. This thing got influenced, the 3 untouched. This is 1/4 as tall as we used to be. The -8 just became -2. All right, and I believe that's page 11. It is. All righty. Now, we are on to the B value. Now, let's think about this. A was a vertical stretch. A made us taller or shorter. H is a horizontal movement, moves us left and right. K is a vertical movement, vertical translation, moves us up and down. Thus, I have taught you how to get taller and shorter. I've told you how to move left and right with H and up and down with K. The only thing left is to make us wide or narrow. And that's the B value. All right? Now, the joke I usually give here is, do you realize that H is backwards? H is weird. X -3, 3 to the right. X plus 4, 4 to the left. Well, isn't that sort of the weird aunt or uncle? And you know that they're going to marry someone who's weird. That's why B and H influence X. And they're the weird aunt and uncle. And then my joke usually here is going to be, do you have any weird aunt or uncles? If you don't, then it's actually your parents who are the weird ones. But then we all have a good laugh on that. So here's the thing you need to realize. While I admit that the B value is clearly going to be a horizontal stretch, yes, this is going to be a horizontal stretch. What I need you to realize is that the horizontal stretch is the reciprocal of B, meaning this thing is not 3 times wider. It's actually 1/3 as wide. This thing down here is not 1/3 as wide. It's actually 3 times wider. So you've got to be very careful with B. B is a horizontal stretch, but B is not the value of the horizontal stretch. B is the reciprocal of the horizontal stretch. Meaning, I don't consider myself fat. I just happen to have a very small B value, right? This thing is now 3 times as wide. So I'm not fat. My B value just happens to be 1/3. All right. So if you want to graph absolute value of x, you're going to get that nice V as in Victor graph. If you graph absolute 3x, you are going to find that this thing will become narrow. When you go and graph absolute 1/3 of x, you are going to find that you are going to get a very wide V. So the B value is a horizontal stretch, but the B value is the reciprocal of the stretch. Big B's makes you narrow. Small B's make you wide. All right, let's come down here. Oh, I literally just said this. Okay, what does the effect of putting a coefficient that is a big B? You make that B value bigger than 1, you become narrow. What happens when your B value is in between 0 and 1? So like 1/3, 1/4, 1/5, you become wide. Now, where are the invariant points? All right, I want you to imagine yourself standing there, and I grab you by your shoulders, and I stretch you apart, or I push you in together. Does your nose move? Whether I pull you apart, your nose is going to stay in the same place. Whether I squish you together, your nose is going to stay in the same place. Meaning, the invariant points are the y-intercept. How come? Because what's the x value? 0. Go ahead, make 0 wide, make 0 narrow. You don't change it. Meaning, the identity of the invariant points are going to be the y-intercept. Given a graph or a point in a graph, how can you determine the coordinates of the new points? Notice, B influences x. So you will simply take the B value and then multiply x by its reciprocal. So up here, all of my x values get multiplied by 1/3. Down here, all of my x values get multiplied by 3. What happens to the y's? Nothing. Right? Given a graph or a point on a graph, how would you determine the coordinates of new points? Well, because this is horizontal, it only touches x. Y is irrelevant in a horizontal stretch. All right, well, hopefully that's page 12. What do we got here? How far are we going? Here's page 13, and here's page 14. Oh, my goodness. All right, well, no problem. All right, yeah, I got this. Okay, so we got some function. What the heck is happening to this graph? Now, some students are going to think that this thing is 2 times as wide, meaning this -2 is going to come out to -4, and I guarantee that there are going to be students who think, whoa, that this thing is going to look something like this. Oh, yeah, out here to 10. Oh, it comes way out here. Well, that is just ugly. But there are students who will think that we are 2 times as wide, and we are not. What this is going to do is take all of my x values and multiply them by 1/2, the reciprocal of b. -2 will become -1. 0 will stay at 0. 2 will become 1. 4 will become 2. 6 will become 3. This graph now looks like this. Sorry, I missed. I gotta fix that. That's just embarrassing. This graph is going to look like, there we go. That's better. Oh, I still missed it. Screw it. You get my point. Notice y's untouched. X's half of what they used to be. Notice that my invariant point is the y-intercept. How come? Half of 0 is still 0. This is a classic diploma. Look, there it is. I got 4s and 8s, and I got a quarter here. Perfect question. Love this question. You got some point Frank, -4, -8. Boom, there is the stretch. Now, I guarantee, I'm just going to start putting some numbers down. There are going to be students who are like, oh, that's 1/4. Maybe it's -1, -2, right? Yeah, everything is 1/4 of what it used to be. That is going to be one of the distractors. No, wrong. Let's just kill that. All right. Then there are going to be students who are like, oh yeah, it's something about like yeah, Chandler said reciprocal. Oh yeah, okay, so it's a -16 and -32, right? Right? Like the diploma knows how to mess with students. Wrong. This is not true at all. Now, yes, this is 1/4, which means the horizontal stretch is actually by a factor of 4. But it only influences x. -4 becomes -16. What happens to the -8? Nothing, because a horizontal stretch does nothing to the y value. All right, but the diploma could have gone on and made this, let's say, some -2, some 32, or they only changed one of them. The diploma's good. We've got to realize that this is a horizontal stretch by a factor of 4. It only influences the x. Thus, we are good to go at a -16, -8. All right, that's page 13. All right, describe the stretch. Okay, got a radical function here. Going to look more at this in chapter 2. Oh, look at that b value. Oh, that b value is a 4. That's a horizontal stretch. Did this thing become 4 times wider? No. It actually became 1/4 as wide, because the horizontal stretch is going to be the reciprocal of b. All right. Now, got a function here, and it looks like the entire function got multiplied by 3. That's an a value. This is a vertical stretch by a factor of 3. Right? Look at that a value out front. This is amazing. I love discussing this one right here. Many students are going to say, oh, Mr. Chandler, I see that as an a value, and therefore that thing is going to be a nice little vertical stretch by a factor of 4. Now, you're going to say to me, well, how do I know it's not the b value? Because it's in front of x. Because notice the x is still being squared, but the 4 isn't. If I had written bracket 4x, close the bracket, squared, then we could call that a b value. All right? So I think that this is a vertical stretch by a factor of 4. Now, what do we got here? This is a nice chapter 3 question. We'll talk more about this in chapter 3. But x got multiplied by 2. X got multiplied by 2. X got multiplied by 2. All right? Now, this is so very cool. All right? You don't know this yet, but this is a cubic function. This thing, when you throw it into your calculator, is going to look like that. All right? I know this. I'll teach it to you in chapter 3. So now you're going to have to decide, are these a values or are these b values? All right? Is the whole thing being multiplied by 2? Well, that got multiplied by 2. That got multiplied by 2. I don't think it did. I don't think it did. I think this is actually a horizontal stretch. This is a b issue, because not everything got multiplied by 2. I think that's a nice looking b value there. So I think this is a horizontal stretch. All right, what happened here? My x got multiplied by 3. Just the x, not the whole function. So I think I'm looking at a horizontal stretch here by a factor of 1/3. Is it not? Now, I want to take a time out for a second and come back to A, because I really want to discuss something. All right. For those of you who know me, I am a tall, rather large man. Okay? I am overweight. I admit that. Now, I want you to think about something. How do I get myself to become the ideal weight based on my body? Well, you could argue, Mr. Chandler, you're overweight. We need to make you skinny. And you can argue that this is a B value, I admit, and you could say that this is a horizontal stretch by 1/4. And I will totally give it to you. I don't mind that. For me to look proper, I need to become skinnier. Now, could you also make me taller? Based on my weight, would I look normal if I was about 8 feet tall? Yeah, because then my weight would make sense for a man who's 8 feet tall. Which means for every horizontal stretch, there is a vertical stretch that does the same thing. And you're going to say, what the heck are you talking about? You see this square root of 4x? Is that not equivalent to the square root of 4, the square root of x, and then the minus 3 stays right here, right? Little math 10, math 20, we can pull this radical apart. Well, what's the square root of 4? 2. Oh, so what does this mean? I could take this radical function and horizontally stretch it by a factor of 1/4, or I could take the same radical function and vertically stretch it by a factor of 2 and achieve the same result. Meaning, every horizontal stretch has a corresponding vertical stretch that would do the same thing. For me to be the ideal body size, you could either squish me together and I'd become skinnier, or pull me taller and I'd then still be the ideal size based on my weight. All right, down here. Did all that. Okay, great. Talk to me about this one. First and foremost, describe using correct transformation terminology the transformations of y equals f of x into this. Right off the bat, I say screw that. This is a +7. Now, I am going to read this out. Here is what's going on. I have a vertical stretch about the x-axis, right? Think about it. You're getting taller. You're making the x-axis stretch, in essence, a vertical stretch by a factor of 6 about the x-axis. Next, a b value of 1/3. That is a horizontal stretch about the y-axis by a factor of 3. I am 6 times taller, 3 times wider. I got a horizontal shift, a horizontal translation, a horizontal movement. Any of those are acceptable. 5 units to the left. +5, left. This +7, I got a vertical shift, vertical translation, vertical movement. 7 units up. I'll say this again. The -7 had to get moved over to the right-hand side. I got a vertical stretch by a factor of 6 about the x-axis. I've got a horizontal stretch about the y-axis by a factor of 3, the reciprocal of 1/3. I got a horizontal movement. I got a horizontal shift, horizontal translation, 5 units to the left, and a vertical shift, vertical translation, vertical movement, 7 units up. Honestly, you do your stretches first, your movements second. I really don't care if you want to do this stretch, then this stretch, this movement, then this movement, as long as you stretch first, move second, always. If you go left to right, you'll never get it wrong. All right, are we on the last page here? I think we are. All right, yes. Okay, so what happens to the graph if x is replaced with 1/5 x? Ah, think about this. What they're saying is, if I had a y equals f of x, That was the original function, is what they're implying. Okay, what happens when that x is replaced with 1/5 x? Ooh, that's a b value. The reciprocal of b is the horizontal stretch. This would make us 5 times wider. 5 times wider. What happens if this y gets replaced with a 7y? Well, we know to get rid of that 7, you got to put a 1/7 over here. If this makes us 5 times wider, this makes us 1/7 as tall. Ah, interesting. Given the domain is from -6 to 3, what happens based on this transformation? Well, isn't this a horizontal? Yes, that's a domain issue. Lo and behold, the horizontal stretch is 3. All of these x's become 3 times wider. So I apologize, this is not going to be the prettiest I've ever done, but my new domain is going to go from -18 up to x, and then up to the 3 becomes a 9. X is still a member of the reals, so here is our set notation. So I'll put this, whee, that's not bad, and then whee, look at that. Oh, that's not bad. But the key here is your domain is influenced by b. You are going to have a b value of 1/3, which makes your horizontal stretch 3 times. -6 busts out to -18, 3 busts out to 9. Now, if they had asked me about the range, range unchanged. How come? Clearly a B issue. Oh, let's talk range. What happens here, given the range of this function is from -4 to 5, here it is in what's known as interval notation. All right, lo and behold, I believe that this thing is going to become 1/4 as tall. Now my range is going to be from -1 to 5/4. Notice that my y's simply changed from what they were to 1/4 of what they were. Now, I don't know if we've ever actually spent some time. This is set notation, and I believe that you are familiar with some set notation. This is what's known as interval notation. Interval notation simply use hard brackets for equal to, and then hard brackets for equal to. So this -4 to 5, if I was to write it as an actual set notation, would have looked like this. Y is a set from -4 up to and including 5, where y is a member of the reals. There she is. So, if you were wondering what those hard brackets are, there's your set notation, where we're familiar with -4 to 5 with the equal to. If it's hard, it means equal to. If it was a round bracket, like if you saw this, round bracket -4 to 5, what that's saying is your range is from -4 to 5, but not including, not equal to -4, not equal to 5. Are you allowed to have one but not the other? Of course. This is saying don't be -4, but you can go up to and including 5. All right, just in case you're not familiar with this interval notation. Not difficult at all. All righty, so what do we got here? If we want to stretch about the x-axis, this is an A issue. If we want to stretch about the y-axis, this is a B issue. All right, so the new equation, if you want to stretch about the x-axis, you'd get y is equal to A f of x. Now, where are the invariant points? When you stretch about the x-axis, your invariant points are your x-intercepts. So x, comma, 0. because go and stretch 0 as much as you want. You're still going to be 0. B, this is going to be y is equal to a, oh, what am I saying? Not a. Make that an f. That's better. Haha, yeah, that was always an f. Bx. And then this is going to be 0, comma y. Because I don't care what you do to 0, you can stretch it all you want. Not much is changing for these invariant points. All right, my students, we got a nice little assignment right here. If you need me, you know where to find me. That was about a 41-minute lesson, so a little longer, but this is a good, solid lesson. Thank you for your time.